Okay, moving on to chapter 3, chemical reactions and quantities, meaning using the mole. Okay, so you do have to be able to balance chemical equations first. That's super important. You can't do the math if you don't have a balanced equation. So we got a couple of tips and best things to remember. Of course, law of conservation of mass. You have to have the same number of atoms of each element on both sides of the equation. Okay, same number of atoms on both sides. That's the most important thing. Now, a couple of tips that I have are to balance your polyatomic ions first, if they stay together on both sides. Balance polyatomics first. It's going to help you out a little bit. Other thing is I would balance pure elements like oxygen, O2, last. Balance pure elements last. And my last tip, if you get this whole even odd situation, like you have an even number of something on one side, odd on the other side, one way to do it is to double everything. So like if this happens a lot in combustion, if you have a hydrocarbon, usually if you double that, then you can rebalance. And if you're still having issues, look for the least common multiple. I'm going to show you an example of that here. So try to balance example number 5 and then check your answers. Okay, this is how I would approach A. Ready? Right now I have 1 phosphorus on the left and I have 2 phosphoruses on the right. So now I'm going to have at least 2 over here. But I'm also going to look at the fact that I have 3 oxygens here and I have 4 here. Okay, that's a whole even odd situation. Now, the only way to get 3 and 4 to balance out, and the least common multiple for 3 and 4 is going to be 12. So I'm going to have 4 of these and 3 of these at the very least, okay? Because now my oxygens are good. And now if I check everything else, actually I have 4 phosphoruses. Well, I've got 3 here, 1 here, we're good. And hydrogens, I have 12, and over here I have 9 plus 3 is 12. I'm actually all good. You don't have to write the 1, that's understood. So this is balanced. Okay, remember I said do oxygens last, so I'm gonna do carbons first. 3 carbons. I need 8 hydrogens, so I need a 4 here. Then we count out my oxygens. Okay, I've got 6 plus 4 is 10, so I need a 5 here. If you have an equation like this in combustion and you're still getting an odd number of oxygens for the left side, go ahead and double your big molecule and then rebalance. That's the best way to do it. Okay, so once you have them balanced, we need to be able to do stoichiometry, big word, right? If you can do stoichiometry, you can solve a lot of problems in chemistry. So first of all, you have to be able to calculate molar mass, or the mass of 1 mole of something, also called the molecular weight, also called the formula weight. So all of these mean the same thing. That's why I wanted to make sure I got them in here. Which numbers are these on the periodic table? Number on periodic table that has the decimals. Right, the other one is the atomic number. We want the number on the periodic table with the decimals that incorporates all of your different isotopes and things. Okay, what is that? Well, it is the mass of 1 mole of something, right? Or 6.022 times 10 to the 23rd particles. And what are the units? They are grams per mole. Or if you're on a really small scale, AMU, most of the time we're going to use grams per mole because that's what we need in our conversions. So little practice before we do the stoic, find the molecular weight of sodium sulfate. Okay, so we do need to break this down. I'm going to do each element individually. Sodium, sulfur, oxygen. Sodium's molar mass is 23.0 and I have 2 of them, so times 2. Sulfur is 32.0 and I only have 1. And oxygen is 16, and I have 4 of them. So I'm going to multiply all of these. So I get 46. Well, 32 is, of course, just 32. Oops. And this is 64. Okay, and then you add to get your molar mass. So the molar mass of sodium sulfate is 142 grams per mole. Now, I didn't give you any numbers in the problem, so there's really no sig figs to go by. I recommend keeping 1 decimal place whenever you're pulling numbers from the periodic table. It's a good rule to go by. Now, of course, the mole. What is a mole? A mole is 6.022 times 10 to the 23rd of anything. Why do we use it? Well, we use it so we can scale up, because usually we're talking when we weigh things, we can get the mass of things, right? You can't actually count out the number of particles. So the whole point of the mole is so we can scale things up to a usable amount. So it's used to scale up or down the number of particles. All right, that's going to be super useful. Okay, so we're going to kind of do a conceptual question first here. Example number 7. Again, pause, answer. You probably already know the answer to this. How many molecules are in 1 mole of CH4? Well, 1 mole of anything, 6.022 times 10 to the 23rd molecules in this case. Now, the important thing to remember is what's called, you probably learned it as a component within. Read questions carefully. The second part says, how many atoms of hydrogen are in 1 mole of this? Well, each particle has 4 hydrogens. So technically, I would have whatever 4 times 6.022 times 10 to the 23rd is, if I'm looking at just the hydrogens. So there are 2.41 times 10 to the 24th atoms of hydrogen in 1 mole of CH4. Okay, read your questions carefully. Okay, so getting to the stoic part, I promise. Mole ratios. Okay, you have to be able to look at an equation and pull your mole ratios, and they are just like a conversion factor. Mole ratio is just a ratio of one species to another from a balanced chemical equation. You have to have a balanced equation in order to do this. That's why that part is so important. The mole ratios you pull from the, sorry, this is getting crooked again, coefficients, that's the important word, in the balanced equation. Okay, big numbers out in front. All right, list the mole ratios that can be used for stoichiometry calculations from the following balanced equation. All right, so this is balanced. I can pull whatever ratio I need depending on the problem. I know that 1 mole of N2 needs 3 moles of H2 for any problem. You can write it, remember, however you need to make your units work out. So you can also write it, there's 3 moles of H2 for every 1 mole of N2. Okay. You can do a reactant to a product. So I can also do that there's 1 N2 to every 2 NH3s. Or you can write it the other way, 2 NH3s to 1 mole of N2. And then your last ones, you can do H2 to 2 H3 or 2 NH3 to 3H2. These are all of the ratios that you can pull from the equation. You just use whichever one you need to make your units work and to calculate your problem. Okay, so I don't know how you learned stoichiometry. You might have done a mole island thing. You might have used a picture, something like this. You might just do dimensional analysis. Any of those ways are fine as long as you show me your work. Essentially, though, the steps for any type of stoichiometry problem. Now, first of all, when do you do stoichiometry? When a chemical reaction happens. Okay, if you have any type of chemical reaction happening and I'm like, how much stuff did I make? Stoichiometry problem. All right, so if chemical reaction happened, I can do my stoichiometry. What are the steps? First thing you always need to do is to convert to moles. Okay, now, yes, if I'm asking for grams and I gave you something in grams, you should be like, well, it's grams and grams. Why do I have to convert? Well, the grams of different things. Always convert to moles. Now, if I give it to you in moles, you can skip this step. But the first thing you need to do is always convert to moles. Then you need to use a mole ratio. Okay, that's what we were just talking about before. Pull that from your balanced chemical equation. And finally, convert back to grams. Usually I'm going to ask for grams. I could ask for volume, right, of gas at STP. You could use the 22.4 or particles. Read the question carefully. What do I want? But these are essentially the 3 steps to a stoichiometry problem. Convert to moles, mole ratio, convert back to grams. Okay, so if I convert to moles, usually, if I'm in mass anyway, that means dividing by the molar mass. That would have meant, okay, my known thing. That would have meant I started here, I converted to moles, so I divided by the molar mass. And then I went to moles of the other thing, right, with a mole ratio. So this is my mole ratio part, okay, mole ratio. Another way to say how the mole ratio should always be set up, I always say it's your wanted over your given. So wanted being the thing you're trying to find, and given being the thing I gave you in the problem. All right, so you're gonna multiply by your mole ratio, and then finally, if I ask for grams, convert back to grams. So in this case, you're going to multiply by the molar mass of your new thing. All right, so example number 9 is just a simple grams to grams stoichiometry problem. And then you should also be able to do volume and particles and all of that. Okay, so give number 9 a try. All right, what mass of ammonia can be produced from the reaction of 2.50 grams of N2? I'm going to start with that over 1 with excess hydrogen. So I have to tell you that there's excess hydrogen because then that means N2 is my limiting reactant. All right, first step, convert to moles. Well, I know that N2 has a, mass of 28 grams per mole. Nitrogen is 14, so N2 would be 28. So now I'm in moles of N2. My next step is mole ratio. That always gets pulled from my balanced equation. So I'm looking back up here. Nope, hang on. I want to do my wanted over my given. So if I started with N2, that means that my N2 moles is going to be at the bottom. And the question is asking for ammonia or NH3. That means NH3 is going to be on top. So my wanted thing over my given thing. Now the numbers I got to pull from my balanced equation. So N2 has a 1 coefficient and NH3 has a 2 coefficient. So this is going to be the 2 moles and this is going to be 1 mole. Okay. Notice these cancel. Then moles of N2 cancel. Now I'm in moles of NH3. The question asked for mass, so I do have to convert back to mass. 1 mole of NH3 has a molar mass of 17 grams. All right, that cancels. That cancels. Now I just got to math it out. 2.5 times 2 times 17 divided by 28, or whatever method you want to type that into your calculator. You're going to get 3.04 grams of NH3. Okay, I did round to significant figures. My number from the problem had 3, so my answer should have 3. Okay,